Won't you explain your neutron interferometer?
You want me to explain an interferometer?
Or just show it and talk about the experiment.
That's kind of hard to do. It has to do with the fact that in nature, particles have a wave-like property as well as a particle-like property. And if you think of the wave-like properties, if you send a neutron beam into a neutron interferometer, and the interferometer, the neutron beam comes in like this, and is split into two beams, one that's reflected off the lattice planes in these little discs here. One goes this way and goes that way, and the other one goes this way, then joins onto the other one. And by affecting the path length of one of the beams, the intensity of the neutrons coming out of the third slab here oscillates as a function of the difference in length of the two paths. If the two paths were at the same level in the gravitational field of the Earth. But if you rotate the interferometer about the incident beam of neutrons coming in this way, then one path goes uphill a little bit, while the other path goes downhill a little bit, and that affects the wavelength of the neutron quantum mechanical waves, and you get an interference pattern. And the idea of this experiment occurred to me in a 2-hour period in 1965. But at the time we didn't know we could make a neutron interferometer out of silicon. That was discovered a number of years later in 1974. And the first interferometer was cut out of a single perfect crystal of silicon, similar to the one I'm holding here with diamond saws, by Roberto Colella, one of my colleagues at Purdue. And remarkably, that experiment, the neutron part of the experiment, was designed by Sam Werner, who was still at the Ford Motor Scientific Laboratory. And the experiment was performed at the research reactor of the University of Michigan in Ann Arbor. And the very first time we did the experiment, it worked. We saw the interference pattern, that is the intensity of the beams coming out the third slab here, would oscillate as a function of how much we rotated the interferometer. And it agreed with the result that you would get or predict if we just put the gravitational potential of a neutron in the Earth's gravitational field as part of the wave equation governing the quantum mechanical properties of a neutron. And so this remains to this day the only experiment where the outcome of the experiment depends simultaneously on gravity as well as quantum mechanics. So it was held into place by its own weight, so we could only turn it about 30 degrees to clockwise or counterclockwise. And it was supported under its own weight, but with these green felt strips to prevent the interferometer from bending even a fraction of the size of a single atom under its own weight. And fortunately, that way of holding the interferometer was discovered 48 hours before we were scheduled to do the experiment at Ann Arbor. And the experiment has now become rather famous. You can even find descriptions of it in elementary textbooks on quantum mechanics. The actual interferometer that was used, that's the first time experiment is shown in this picture. The ears that reflected the neutrons weren't chopped off as it was done here, to minimize the bending of these ears under their own weight by gravity. This is a picture of the inside of the box, which kept temperature stabilized to thousands of a degree centigrade. And here is the interferometer here, the first leaf, the second leaf, and the third leaf. These things over here are neutron detectors, and the neutron beam is coming in this direction, getting Bragg reflected, partially Bragg reflected at the first slab, and then both beams were reflected at one. Well, anyway, the beams were split apart into two pieces, and then recombined over here at the third slab, where the interference pattern could be observed. The oscillations that I'm talking about are quantum mechanical oscillations of the combination of two beams which are coherent with one another. And it's one of the major mysteries of quantum mechanics, which nobody really understands, but it's the truth. And as I've already mentioned, this is the only experiment where the outcome, namely the number of fringes in rotating the crystal a certain angle, depends on Planck's constant, the constant that comes into quantum mechanics, and the gravity constant that comes into the attraction of all two bodies in the universe by their mutual gravitational interaction. And this is an actual picture of the interferometer that Roberto Colella carved with a diamond saw out of a single crystal of silicon that was circular in cross-section and about as long as the distance between my thumb and little finger.
So, tell me about high school.
About what?
High school.
High school?
Yes.
Oh, well, I grew up in San Francisco and was very involved in music from the time I was 10 years old. I played in dance bands and orchestras and marching bands, and that took a lot of my time, especially away from my academic studies in junior high school. And in order to, growing up in San Francisco during the decade when the two main bridges were built, the San Francisco-Oakland Bay Bridge and the Golden Gate Bridge across the Golden Gate, my desire from watching those bridges go up was to become a civil engineer and design bridges. For frequently had all the books on bridges out of the library, which was next door to the house where we lived. But in order to get away from the music scene and prepare myself for becoming a civil engineer, I went to Wilmerding High School, which was a private school. The Lick is the same Lick who built the Lick Observatory in California for astronomy. But in Lick Wilmerding High School, they had a fantastic physics teacher. I didn't know what physics was. I'd never heard of the word. But this teacher was so good that I immediately decided to become a physicist instead of a civil engineer. So that's how I got into physics. I graduated from Lick Wilmerding in 1942, enrolled at the University of California in Berkeley, and spent 2 years at Berkeley before enlisting in the United States Navy. So I spent the years from 44 to 46 in the Navy studying electronics. I became an electronics repair person for radar, radio, sonar, long-range aids to navigation, and so forth. So when I got out of the Navy after the war ended in 1946, I went back to Berkeley and graduated in 1948, but I then immediately enrolled as a graduate student at Berkeley and received my PhD in physics in 1951 after 3 years in graduate school. So that's how I became a physicist. It was all because of the inspiration of a really wonderful physics teacher. I had 6 courses in physics in high school. Believe it or not, there were that many that one could take at Wilmerding.
How did you meet Margaret and get married?
Why do you bring that question up? Well, when I was a graduate student at Berkeley, she was an undergraduate. She had graduated from Pasadena City College, which is sort of a junior college, and then came up to Berkeley to do her last 2 years of study to get her bachelor's degree in chemistry. And I met her because we belonged to the same organization at church, and that's how we met.
And tell me about the Overhauser effect.
Well, the Overhauser effect is something I discovered in a couple of days of work. My PhD thesis was involved the electron spins of electrons in metals. Metals have electrons that run around freely. They're not bound to particular atomic nuclei. And electrons have a magnetic moment, so if you put them in a magnetic field, the energy of the electron splits up into 2 possibilities. One spin up, the other spin down, up and down being parallel or anti-parallel to the magnetic field you're putting on. And electron spin resonance corresponds to exciting transitions from the upspin state to the downspin state, or vice versa. It usually uses microwaves for fields of the order of several thousand Gauss, which is the unit of field strength in those days. With the electron spin resonance of various materials had been discovered in recent years then, but nobody was able to find the electron spin resonance of the conduction electrons in lithium metal. And they didn't know whether that was because the electron spins were flipping too fast or whether the experiment was bad. And so my job for a PhD project was to study all the mechanisms that could cause the electron spins in lithium metal to flip it from up to down or down to up. And after I got my PhD at Berkeley, I got a job as a postdoctoral research scholar at the University of Illinois. And I was working as a postdoc on radiation damage to metals, because in those days the design of nuclear reactors was involved choosing the right types of metals and alloys to make the reactors safe and not deteriorate from radiation damage caused by protons and neutrons. But there was a seminar course going on at the University of Illinois on magnetic resonance. There were 5 people in the faculty who were in the field of magnetic resonance. And as a result of listening to those seminar talks, I wondered what would happen to the nuclear spins in lithium. Nuclei have little magnetic moments too, but they're usually 2,000 times smaller than electrons spin magnetic moments. And when you hit the electron spin resonance, you're driving the electron spins out of equilibrium with respect to the ambient temperature of the metal. And I became curious as to what happens to the nuclear spins when you drive the electron spins out of equilibrium. And I did that calculation in a couple of days because I knew how to do such things. And surprisingly, if you hit the electron spin resonance strongly, the nuclear spins enhance their magnetization by a factor of 1 to 2,000. And that's what came out of my calculations. People didn't believe that. They thought I was violating the laws of thermodynamics by saying that. So one of the professors at Illinois who believed my calculation decided to do the experiment and see if that happened. And it took them about 1.5 years to build the equipment necessary to do the experiment, where you both excite the electron spin resonance and then also look at what happens to the nuclear spin resonance to see whether it changes by factors of 100 to 1,000. They eventually did that experiment, but I'd already left Illinois to become an assistant professor at Cornell University. And a week after I got to New York, I received a telegram from Charlie Slichter, the professor at Illinois who was doing the experiment, announcing that they had done the experiment, and the very first time they tried it out, the nuclear spins became polarized by exactly the amount my theory predicted. And this was a remarkable phenomenon. Most people didn't believe it was possible. And but it worked out, and that phenomenon is known as the Overhauser effect. When we drive the electron spins out of equilibrium, the electron spins also are involved, they interact with the nuclear spins, And if an electron spins that way and a nuclear spins that way, and you can induce transitions where you flip one and flip the other. And these are the transitions that play a role in the origin of the Overhauser effect. You can also do it with nuclear spins of two different species. The original Overhauser effect was involved in hitting the electron spin resonance and seeing what happens to the nuclear spins. You can also do a similar experiment where you hit a nuclear spin resonance of one species of atom and look at what happens to the nuclear spin resonance of another species of atom. And that's called the nuclear Overhauser effect. And it's used to study the structure of complicated molecules, because that interaction depends sensitively on the distance between the two nuclear species you're looking at. And that nuclear Overhauser effect has been used extensively by structural chemists to determine the structure of important large molecules. And several books have been written on these applications. Here are a couple of them. And
And you talked about the Overhauser effect at any conferences before the experiment was done?
I went to a physical society meeting in March of 1950. I guess it was March of 19. I forget the exact date. And I gave a 10-minute talk where I announced the prediction of this dynamic nuclear polarization, as it came to be called. And sitting in the front row, listening to me give this 10-minute paper predicting this sensational effect, were three of the giants in magnetic resonance: Ramsey from Harvard, Purcell from Harvard, Felix Bloch from Stanford, and Isidore Rabi from Columbia University. And after my 10-minute talk, they concluded that I was violating the laws of thermodynamics, and therefore this effect wouldn't exist. Well, they changed their mind as a result of the experiment working out successfully. And those four people I mentioned all have Nobel Prizes. And so I didn't want to argue with them. I said, well, it doesn't matter what they think. I don't think I violated the laws of thermodynamics. But the experiment was going to be done in the near future, and let facts settle the matter.
What experiments do you still want to do?
What experiments do I want to do? Well, one of my most important theoretical discoveries was in what happens to metals as a result of the Coulomb interaction between the conduction electrons. It leads to a new type of ordered state, which can be either a spin density wave or a charge density wave. I brought a picture of that. Yeah. Here I've plotted the electron density as a function of position in a metal. and the shading, that the vertical shading and horizontal shading are meant to indicate electrons with upspin and electrons with downspin. And what I discovered theoretically was rather than just have a uniform density of spins and a uniform density of downspins, the metal liked to have what I call a spin density wave, which is depicted here, where there's a sinusoidal oscillation in the upspin electrons and a similar sinusoidal modulation in the downspin electrons. And so if you calculate the spin density in any position, there will be an oscillation in the spin density as a function of position. And I call that a spin density wave. And I actually proved in a fairly standard approximation used in theoretical physics that this type of phenomena should always occur. But there are two possibilities. What is shown here is a spin density wave. If you move, say, the downspin electrons by half a wavelength to the right, then the peaks will fall on top of one another, and so in that case the upspins and downspins lead to zero spin density, but lead to a charge density wave, and that state of affairs I call it a charge density wave. So spin density waves or charge density waves were new states of electrons in metals that I discovered theoretically. Nobody believed in those things either. But spin density waves were first observed in chromium metal, and charge density waves occur in a number of metals. And these broken symmetry states, as they are called, lead to lots of strange electronic properties which no one in the world can explain. Here's a list of 30 strange phenomena that have been observed experimentally